Hello all. This video is made with the combined efforts of Ms. Lipsa, Ms. Jessie, and myself, Mr. Ashok, EC Department of New Horizon College of Engineering, Bangalore. So in this video, we'll be discussing about the frequency shift key, the generation and its detection, as well as the implementation of the circuit in Multisim. So by reading the specifications of the circuit diagram, we will be able to generate the proper waveforms in Multisim. So this is the second prominent modulation technique that is being used in high frequency RF communications. But this is having higher, that is, it requires more bandwidth. This type of modulation techniques requires more bandwidth. So this is less used for high speed applications. So FSK type of generations or modulation techniques, they are mostly used in high frequency applications but with low speed modems, particularly with low speed modems of about 1200 bits per seconds as speed. So whenever this FSK is concerned, as from the name itself, the frequency of the carrier signal is being altered with respect to instantaneous values of the message signal. Again, this is of digital modulation technique where the input message will be of digital data, which is represented by a square waveform M of t, and this is being modulated by the carrier signal C1 of t and C2 of t. So here we require two carrier signals of two different frequencies. So here we have taken 2 kilohertz frequency as well as 4 kilohertz frequency as two distinct frequencies for the modulation. So as per the circuit diagram, here we need two transistors performing the high power switching. One is SL100, which acts as an NPN transistor. Similarly, SK100, which is complementary to this SL100, that act as PNP transistors. So simultaneously, the message signal M of t is going to the base of the two transistors, and we are taking the FSK output across a particular resistance that is connected at the emitters of the two transistors, where emitters are being short circuited. And note that the two carrier signals is given to the collector terminals of the two transistors. So here at a time only one transistor will be on, and meanwhile the other transistor will be off. So whenever your message is logic 1, that is high voltage, the NPN transistor will conduct, it is forward biased, and meanwhile your PNP transistor is off. So as a result, the carrier signal C1 of t, which is of high frequency, will come across the emitter terminal of first transistor, which is eventually coming across a load resistance of 1K. So the FSK output will be same as that of the carrier frequency C1 of t whenever your message is 1. At the same time, when the message is 0, the first transistor will be off. Meanwhile, your PNP transistor will conduct, and as a result, the carrier signal C2 of t, which is comparatively lower than that of C1 of t, will appear across the resistance RE. And now the FSK output is same as that of the frequency of C2 of 2 whenever your message is 0. So likewise, when the message is switched from 1 to 0, as well as back from 0 to 1, your frequency of the carrier is being switched from C1 of t to C2 of t. As a result, this is known as frequency shift keying. I would like to show the waveforms. See here, this is your message signal. Typically, you have 500 hertz, which is to be transmitted from the center to the receiver. And you need two carrier signals, 2 kilohertz and as well as 4 kilohertz. So this is C2 of t as well as this is C2 of t and this is C1 of t. So whenever your message is high or logic 1, the high frequency comes to your output, and at the same time whenever your message is 0, the low frequency comes to your output. So this is what is a FSK output. Now going to the design part of the circuit diagram. So like ASK, here also you need to have some demodulation as well as modulation technique. Now I would like to explain demodulation and then we will go to the design section. So as of now we got the FSK output. Now this FSK output we need to demodulate or detect at the receiver side so as to extract the original message signal. For that, initially in the detector side you will have a low pass filter, because when you observe the FSK waveform you always have the combination of the high frequency as well as low frequency in the respective time slots. So since we are interested in the low frequency signals for the detection of the message, so we will be passing the low frequency signals alone and attenuating the high frequency. For that, we will be using a low pass filter at the input stage of the detector. So the intention of putting this low pass filter, which is a combination of R1 C1, is to pass the low frequency waveform of the FSK output and attenuate all the high frequencies. Now, when you have a low frequency signal, it is to be rectified, means your negative half cycles to be eliminated on that can be ensured by using this diode. So this diode will be passing only the positive half cycles or positive cycles of the input low frequency signals, which is then smoothened by using a combination of resistance and capacitance. So the combination of this RC should ensure that the frequency 1 by RC, that is the frequency corresponding to the time constant of this RC circuit, should lie between the two carrier frequencies FC1 and FC2. So that is to be ensured. See, FC1 should be very much less than 1 by RC, should be very much less than FC2. So if it is 2 kilohertz and 4 kilohertz taken as the two carrier frequencies, your value of 1 by RC should lie between 2 kilohertz and 4 kilohertz. That is to be ensured. Only then you will be having a low frequency smoothened waveform, which is to be coupled to the positive terminal of the op amp. So at the end of the detector part, you have a comparator, which is nothing but an op amp that is used to compare the input signal with the reference signal. So here the reference signal is being set by using a potentiometer. So by varying this potentiometer variable terminal, we will be able to set an appropriate reference voltage at a particular point of time. You will be able to compare your reference with the input signal and you can decide the message or detect the message. Okay. So varying this potentiometer only at a particular point, you will be able to detect this M of t, where the frequency of the detected signal M dash of t should exactly match with the message whatever we have transmitted from the transmitter side. So this is the detector part of the FSK side. Now going to the design. So when we go to the design here, obviously we need to design the value of resistance RE that is connected to the emitter terminals, as well as the base resistance connected to the two bases of Q1 and Q2, that is two transistors. Okay, so this 10K is to be designed as well as this 1K is to be designed. So for that, consider this as RB and consider this as RA. So for that, applying KVL to the output side initially. So output means you're having the collector, isn't it? So collector voltage VC peak is equal to VC sat plus IERE. So VC peak is the peak voltage of the collector terminal, which is equal to collector emitter junction voltage plus the drop across resistance. That is, you are applying KVL to the either one of the circuit, because you know that only one circuit is on at a time, meanwhile the other transistor is off. So you just want to apply KVL in any of the output circuits related to SL100 or SK100. So if you consider this as your loop, so this is your collector voltage, isn't it? This is your collector voltage. Okay, so that collector voltage is equal to the junction voltage, that is VCE, plus the drop across resistance, that is IERE. Meanwhile this SK100 will be off. So that is what is being written over here. Okay, so if you are taking this collector voltage or the carrier voltage as 5 volt peak to peak, obviously the peak value is 2.5 volt, which you can substitute instead of this VC peak. Okay, and meanwhile you have taken a transistor whose beta value is 30, as mentioned here, HF is 30, and you know what is VC, and you can take this VC sat as 0.2 volt, that is saturation voltage of the transistor, and solving this you will get RE, provided the IE is given. IE of this transistor is 1 milliampere according to the data sheet. So now solving this equation, you will get RE around 1 kilo ohm. So this is the equation or the design value of resistance RE across which you have taken the FSK output. At the same time, to find the resistance RB that is connected to the input terminal, you have to apply KVL to the input side. So in the input side also you're having a message signal. Probably you would have set as it as 5 volt peak to peak. So normally it will be 2.5 as your input, or if you are taking 2.5 volt peak to peak, it will be 1.25. so that you can relate with respect to your carrier signal. Okay, so as of now we have taken 5 volt peak to peak as a message signal, so obviously 2.5 volt peak as the message. Now this is to be designed, so the drop across this resistance is IBRB. So VM peak is equal to the drop across RB, that is IBRB, plus a junction voltage. Junction voltage is VBE plus the drop across IERE. Consider SL100 is the only transistor that is conducting at a point of time. Meanwhile, SK100 is off. So don't consider this lower part. So just apply KVL in this circuit. Understood? So VM peak is equal to the drop across RB, that is IBRB, plus the junction voltage VBE plus the drop across RE, that is IERE. As of now, you have IE with you because it is given in the data sheet as 1 milliamps. RE already we have sold for RE, that is 1 kilo ohm, which can be substituted. VB is 0.7 volt for a conducting transistor, and you can find IB because IE is equal to IB plus IC. You can substitute IC as beta IB. Beta is given as 30, so sold for IB. That IB you can substitute over here. Okay, by simple transistor equation, you can find that IE is equal to IB plus beta IB, or IB is equal to IE the whole divided by 1 plus beta. So by using that relation, we will be able to solve IB and substitute in this equation so that the only unknown RB can be solved around it as 10 kilo ohm. So as of now, you have the base resistance as well as the load resistance RE. So that is a design part of this modulation circuit. And again, we can come to the demodulation circuit where you will be using the envelope detectors as well as the low pass filter. So while designing this low pass filter, you should have the equation, that is Fc is equal to 1 by 2 pi Rc, where we are interested to pass only the low frequencies. So out of the two carrier frequency, one you have set it as 4 kilohertz, the other you have set as 2 kilohertz, out of which the low frequency is 2 kilohertz. So you should be able to design a filter so as to pass the low 2 kilohertz frequency along and attenuating the high frequency component, that is 4 kilohertz, because the FSK output, it has the combination of both 2 kilohertz as well as 4 kilohertz. So this low pass filter is able to pass the frequencies of 2 kilohertz, which is being designed by using this equation 1 by 2 pi RC is equal to FC1. So choose the value of C1 and R1 approximately so as to pass the 2 kilohertz along. Then coming to the envelope detector side, because here this is going to detect the, or it is going to improvise or smoothen your input signals to the decision making device. So for that, for the exact smoothening, the frequency corresponding to this time constant, that is 1 by RC, should lie between FC1 and FC2. That is, it should be between 2 kilohertz and 4 kilohertz. Likewise, when you choose this resistance as 10 kilo ohm and this capacitance is 0.1 microfarad, not necessary that you have to use these two values, because while simulation you can change those parameters in such a way that this condition, particular condition, is being satisfied, so that it will be produce an accurate smoothened waveforms which is able to detect a proper message signal by using an appropriate decision making comparator. So this is what is the design of this particular section, that is demodulation part. Now we will move to the simulation side. So I have used a Multisim software for the simulation part. So the same circuit, whatever we have designed, I just put as a circuit. So here we have, obviously we are having the two transistors and the two resistances, whatever we have designed, that is R1 and R2. And this is your low pass filter section, and this part is your envelope detector side, and this one is your comparator, which is acting as a decision making device. And you're having two signal generators, three signal generators, that is two carrier frequencies as well as a one message frequencies. So I would like to show the message frequencies and its parameters. So this one is by double clicking in this function generator, it will show that frequency is 500 hertz, and you have given us 3 volt peak to peak, 3 volt peak signal. And at the same time, the two carrier frequencies, that is one it is 10 kilohertz I have taken, and the other one it is 2 kilohertz. Okay, so one is of low frequency, the other one is of high frequencies. Now I just try to run and show the input waveforms first of all. So after running, you double click the first CRO. So these are the four oscilloscopes. So when you double click the first CRO, it will be showing your input signals, that is the square waveform as well as one carrier frequencies. So this is your message, square is your message, the sinusoidal waveform is your carrier frequencies. Now at the same time, this is your FSK output which is taken across this 1K resistance, that is the emitter resistance. So once you stop this, you can see that a high frequency waveform is coming along with low frequency, isn't it? So this low frequency corresponds to your message 0, and this high frequency, that is 10 kilohertz waveform, corresponds to the message 1. So for high you are having high frequency, for low voltage you are having low frequency. So this is what is the expected FSK output. So I will try to compare this with respect to your message signal so that you can track the original FSK with respect to your message. So for that, what you will do is take the second oscilloscope. So one of the channel, that is channel B, you can connect to your signal generator of message signal. So this is your message. So I'll be connecting to this particular point so that I can compare. Sorry. Okay. This is your second channel. So I'll be taking this second channel output to the first signal generator so that your input comes to the second channel, as well as FSK output you are taking from the emitter terminal of the transistors. So after running, now you will be able to see your input frequencies as well as your FSK output simultaneously. See, now by putting in the reverse mode, I will be able to see it very clearly that for low frequency, that is for low message, you are having low frequency, and for high value of the message, that is for logic 1, you are having high frequency. So this is your frequency shift keying waveform. Now going to the detector side, that is a third CRO. After double clicking it, see, this is your smoothened waveform after the envelope detector. Now this is going to the input of the op amp, which is the actually acting as a comparator. So this is your potentiometer, a 10K port I have used, and this is the variable slot which you can vary to get the accurate output. Okay, so as of now I have set this with 2% no, so that you will get a proper waveform at the output. Okay, so this is your demodulated output which is connected. So this particular CRO I have connected to the output pin of your op amp, and I would like to measure the frequency of this particular demodulated output, and I should validate that it is same as that of your input frequency. So this is your time marker, and you can set your cursor appropriately at the end and starting and the end of your waveform, considering one single cycle. And this is your T2 minus T1. See, it is showing 2 millisecond. 2 millisecond is nothing but your 500 hertz. So the demodulated output frequency is 500 hertz, which is exactly same as that of the input frequency. I would like to show the input frequency. See, this is 500 hertz. So now I can say that my communication system is effective and it is able to reproduce a message signal whatever I have transmitted. Now I would like to change the input frequency and see the same thing I am trying to get at the output. So I will be setting it as 1 kilohertz. So now my circuit should be able to recover this 1 kilohertz frequency. So I have set the input waveforms, stop the simulation and again rerun. Okay, check the input frequency. It is 1 kilohertz. Now find the output. Again, by using the cursor, you can set your end limits, and this value of T2 minus T1 is again see 1 millisecond. So it is tracking your input. So whenever there is a frequency change in your message, it is recovered at the output so that this FSK demodulation circuit is working properly. Thank you.